Hello there, this is Ms. Page, and in this lesson we are going to talk about how to graph polynomial functions from standard form, specifically using the zeros and the end behavior. So one of the things we have previously learned is how to factor a polynomial with 4 terms using our strategy of grouping, to where we put them into pairs, the terms into pairs, and here we're using the first two and the second two, and we factor the GCF out of each pair. So here we have x squared as the first GCF, and that gives us times the binomial of x plus 5, and in the second pair our GCF would be -4, and then that gives us times the binomial of x plus 5. And we've learned that in the next step what we're looking at is this binomial of x plus 5 now acts like a common factor between these two products. And so we can factor out the x plus 5, and then that would be times what's left, which would be actually the GCFs that we did in the first step, the x squared minus 4. And then we've talked about the necessity at this point to examine our binomials to see if they are any of our special binomials that we can factor. This is a difference of 2 squares, which factors into these binomials, but it also might be a sum of 2 cubes or a difference of 2 cubes. All right, so what we're looking at here is using our knowledge of what we did in the previous lesson, where we graphed from factored form. That we know that the end behavior of a polynomial function is determined by 2 characteristics that both come from its first term in standard form. And that term we had to calculate in the previous lesson because we had the factored form. But given standard form, we don't have to do that. We just need to know how to interpret it for our information. So remember that we need to know the degree, if the degree is even or odd, and that tells us whether the ends go the same direction, even degrees, or opposite directions, odd degrees. And we need to know the sign of the leading coefficient, whether it is positive or negative, and that tells us which direction the right end goes. So if it's positive, the right end goes to positive infinity. If the leading coefficient is negative, the right end goes to negative infinity. And that is what this is about. So we've seen this before also, that our odd functions, or our odd degreed functions rather, their end behaviors go opposite directions. So one goes to positive infinity, the other goes to negative infinity. If the leading coefficient is positive, then the right end goes to positive infinity. If the leading coefficient is negative, the right end goes to negative infinity. And for our even degreed functions, then the ends go the same direction. So they either both go to positive infinity or they both go to negative infinity. If the leading coefficient is positive, the right end goes to positive infinity, so the other one does too. If the leading coefficient is negative, the right end is goes to negative infinity, so the other one does too. So this is just a step-by-step process, basically what we'll be doing. So we'll determine the end behavior using the first term that's in standard form. So we're looking at from our standard form here to determine the end behavior. And we have to use the first term of our standard form. Then we'll use our factoring skills to factor the function. And from that, then from those factors, we'll be able to find the zeros. So once we've factored it, it will be what we did in the previous lesson to find the zeros using our zero product property and so on. And then with those 2 pieces of information, we will sketch a smooth curve that represents the polynomial function. All right, so here is our first problem. For each of these polynomial functions, we are going to state the end behavior, which means to use our end behavior notation clearly and completely, state the values of the real zeros and include any multiplicity, which we can do either by, in parentheses, stating the multiplicity factor, or we can just write it multiple times, write the zero multiple times. And then, of course, we have to sketch the graph. So this is what we're looking at working with. So the first term is identified as the term that has the highest power of x. So that would be our negative 2x cubed. So our first term is this negative 2x cubed. And so what we have here is an odd number for the degree, and that means our ends are going to go opposite directions, one up, one down. And the sign of our coefficient being negative means our right end is going to negative infinity. So that end, that right end, would be as x goes to positive infinity, our function values, f of x values, are going to go to negative infinity. And because the degree is an odd number, then that means the other end, which is as x goes to negative infinity, has to go the opposite direction. So f of x values go to positive infinity. All right, second thing we want to figure out is what our zeros are. So here's where we're going to have to use our factoring skills. So you can factor with the f of x, or you can factor after you let the f of x be equal to 0, because you're finding x values that create a function or y value of 0. So this would be 0 equals, and then you want to factor this expression. So there's a GCF of negative 2x squared, and that would be times then x plus 6. And x plus 6 is not a special binomial, so that means that we're going to be done with our factoring. So now we can use our zero product property, but one of the things I want to point out is your x squared here, that is a repeated factor. So this, remember, we think of as negative 2 times x, and then that's times the x plus 6. So my zero product property, negative 2 can't be 0, so I'll ignore that. X equal to 0 is already equal to 0, so that means x, or actually it means that if we're already x, then 0 is one of our zeros. And then we have another x equals 0, so we have that repeated 0 of 0. And then we have x plus 6 equals 0, and subtracting the 6 gives us x equals negative 6. So our zeros are negative 6, 0, and 0 again. Let me fix this because I don't know what that says, but it's supposed to say zeros. All right. So what we're looking at now is completing the graph. So getting our axes, we want to make sure that we draw our y-axis so that we can reach negative 6, but not that big a deal here. A lot of squares for us to work with. So this is negative 2, negative 4. Here's our negative 6. And then 0 is our origin, and that is where we have some multiplicity. So we'll have either a relative maximum or relative minimum, and we'll know that after we kind of take a look at our end behavior. So going back to our end behavior, the left end is x goes to negative infinity. The function values were going to positive infinity, so that's over here. And as x goes to positive infinity on the right end, the function values are going to negative infinity, so it's down here. So that means that from here we're going to trace through, go right through this one, and then we're coming up at that multiplicity 0 from the bottom, so that means it's going to be a relative maximum. So I'm just going to finish from there And there is a sketch of this particular function. All right, let's take a look at what is next. All right, so here, same thing. Here's the function that we're going to work with. And so here we're looking at, again, figuring out our end behavior from our first term, which would be that x to the fourth term, negative x to the fourth. So that first term is negative 1 x to the fourth, or just negative x to the fourth. And of course, 4 is an even number. So we have an even degree function. And that means our ends both go the same direction. And since our leading coefficient is negative, both ends are going to go to negative infinity. So the left end, as x goes to negative infinity, our function values go to negative infinity. Come on. And as x goes to positive infinity, f of x goes to positive infinity. Whoops, negative infinity. Same, both negatives. All right, so now we're looking at our zeros. So in order to figure out our zeros, we are going to need to set f of x equal to 0 and factor the right side of this function as much as possible. So we have 0 equals. Here I notice my leading coefficient is negative. Some of you I know might be comfortable factoring with a negative x squared and a positive x squared. I'm going to factor out a negative 1 myself, and that changes the sign. So the negative here becomes positive. The positive on the 15 becomes negative. And the negative on the 44 becomes positive. So this trinomial is one that we have learned how to factor to where it has a quadratic structure. So we'd use factors of x squared for our x to the fourth. So we'd have x squared and x squared. And then we need 2 factors of 44, both of which need to be negative. That will also give us this negative 15. So we're looking at, okay, well, we have 4 and 11. And actually, 4 and 11 should work because a negative 4 plus a negative 11 will be our negative 15. So we have that. All right, so now what we're looking at is x squared minus 4 is a difference of 2 squares. We could factor it further if we wanted to, but since we are solving for values of x and our goal is not necessarily to factor, we could stop here and be able to use our square root property on both of these. We can't factor x squared minus 11 anymore anyways. So I'm going to stop and use my zero product property. Negative 1 can't be 0, so I'm going to ignore that one. X squared minus 4 could be 0. And if so, that gives me x squared equals 4. And that gives me x equals plus or minus the square root of 4, which is plus or minus 2. And the other one, x squared minus 11 equals 0. Adding 11 gives me x squared equals 11. And taking the square root gives me plus or minus the square root of 11, which is irrational. So my zeros here, of which I have a total of 4. I have negative square root of 11, negative 2, positive 2, and positive square root of 11. That's least to greatest. You may or may not realize that yet because we haven't talked about approximating the square root of 11. But since 11 is bigger than 9, it's going to have to be larger than 3. And that's going to have to be smaller than negative 3. So that's the next thing I'm going to want to do is I want to approximate this. So I know my square root of 11 is between the square root of 16 and the square root of 9. That's a 3. That's a 4. The difference between 11 and 9 is 2. And the difference between 16 and 11 is 5. So that tells us that, okay, 11 is much closer to 9 than to 16. So the square root of 11 is much closer to 3 than it is to 4. So I'm going to say it's about 3.3. So we have a negative 3.3 for this one and a positive 3.3 for that one as far as an approximation. So now I'm going to go back to my graph here, draw my axes in. So I have zeros at positive 2 and negative 2, and then about 3.3 and negative 3.3. My end behaviors are both to negative infinity on the left and the right. There's no multiplicity, so I'm just going to start here, and the curve is just going to move smoothly through all of its zeros, and there's a sketch of our graph. All right, let's take a look at another problem. So here we have a practice problem. Please pause your video, give this problem a try. All right, let's take a look at what we should have here. So here we see our first, does it talk about? It doesn't. So here's our first term. It's actually the same first term that we were working with. So we are dealing with an even degree. 4 is an even number. So the ends go the same direction, and our leading coefficient is a negative number. So both of our ends are going to negative infinity, as we see here. With our zeros, this time in factoring it, we have not just a common factor of -1, but we have x squared also in common. So we have a negative 1x squared, and that gives us the trinomial here that factors into these two binomials. So we have, this is done a little bit differently here. The way that we've been doing it is splitting this into x times x and then our -1. So our -1 can't be 0. And if x is equal to 0, then 0, and we get another 0 for zeros, and then we get the -5 and the 1 to complete it. So we do have multiplicity here. And so this is the actual graph, so you can see your curve probably looks different from this, but the idea is still the same. You might have done something more like this. But this 0 of 0, which has the multiplicity, does have to be a relative minimum. All right, let's see what's next. Okay, another example for us to do together here. So we are looking at a polynomial function here with 4 terms, but we still would use the first term to figure out our end behavior. So our first term is x cubed, not because it's in the first position, but because it has the highest power of x. In standard form, that term will be in the first spot, but if it's not actually in standard form, then it doesn't have to be. So if our first term is x cubed, then we have an odd degree exponent, and our leading coefficient is a positive 1. So that means our right end goes to positive infinity, and because our function has an odd degree, the other end goes the opposite direction. So the right end is as x goes to positive infinity. Let's see if I can write that a little bit better here. So as x goes to positive infinity, our right end, f of x values, go to positive infinity to match the sign of the coefficient. And the left end, which would be as x goes to negative infinity, those function values have to go in the opposite direction because of the odd degreed value, and that would be negative infinity. So there's our end behavior. So now looking at finding our zeros. So we have our function here, f of x equals. So this goes back to the prior knowledge I was refreshing our memory on. We have 4 terms. We'll use our grouping strategy. We'll let f of x equal to 0, and then I'm going to put these into pairs. And so the first pair has a GCF of x squared, and that would be times x plus 1. The second pair has a GCF of negative 34, and that would also be times x plus 1, which, if you recall, is absolutely necessary that these binomials be the same for us to continue with the factoring, because now that x plus 1 is a common factor that we factor out here, and then it's times the second binomial of x squared minus 34 that comes from the GCFs. So now I can use my zero product property. So either x plus 1 equals 0, in which case subtracting gives me a 0 of negative 1, or I have x squared minus 34 equals 0. Here I'm going to have to add 34 to both sides, and then use my square root property. So taking the square root of both sides gives me plus or minus the square root of 34. Now 34 is not a prime number, but it is the product of, it's even, so it's 2 times 17, and 17 is prime. So it's the product of 2 different prime numbers. That tells us we can't simplify the square root of 34 at all. So our zeros are equal to our negative square root of 34. Try to write that a little better. Our negative 1 and our positive square root of 34 from least to greatest. All right, so now in order to graph those irrational zeros, we're going to have to approximate them. So 34 is between the perfect squares of 36 and 25. So the square root of 34 must be between 5 and 6. The difference between 36 and 34 is 2. The difference between 34 and 25 is 9. So that's telling us 34 is a lot closer to 36. So the square root of 34 is a lot closer to 6. So I'm going to say it is probably about 5.8, 5.9, somewhere in there. So that's going to give us a negative 5.8 and a positive 5.8, or 5.9 if you prefer. All right, so now going back to our graph here. My x-axis here, my y-axis in the middle should be fine. All right, so we have our negative 5.8, 1, 2, 3, 4, 5, so right about there. And negative 1, which is there. And then positive 5.8, 1, 2, 3, 4, 5.8. There. And our end behavior, our left end is going to negative infinity. Our right end is going to positive infinity. No multiplicity, so it just curves through each of the zeros nice and smoothly and keeps going. All right, that finishes this one. Let's see what's next. All right, so here is a practice problem. Please pause the video and try this one. All right, let's take a look at the results here. All right, so here our first term is also an x cubed, so it has the same end behavior as the problem that we were doing. Left end goes to negative infinity and right end goes to positive infinity. Here's the factoring shown right here. So grouping GCFs, and then x minus 2 is a common factor times x squared minus 17. And then your zero product property gives you zeros of 2 and positive and negative square root of 17. Being a prime number, it can't be simplified. And your square root of 17 is between 16 and 25. So square root of 17 is between 4 and 5. 17 minus 16 is 1. 25 minus 17 is 8. So you can see it's a lot. 17 is a lot closer to 16 than it is to 25. So the square root of 17 is a lot closer to 4. And it's about 4.1. So then we graph those and draw our curve. All right, here's another practice problem to try. Let's take a look at this one now. So here our first term is x to the 4th. So it's an even degree. 4 is an even number, so both ends go the same direction. And the coefficient is positive 1, so that tells us both ends go to positive infinity, which is what we're seeing right there, and we can see it here in our graph. Also, this trinomial has a quadratic structure where we'd use x squared and x squared as our factors for x to the 4th. And for positive 32, you should have used negative 16 and negative 2. This one shows factoring x squared minus 16 into x plus 4 and x minus 4, which is fine, but you can also have used the square root property on it, like was used here on x squared minus 2, which would not factor because it's not a difference of 2 squares. Either way, you should have come up with 4 zeros, negative 4, positive 4, and then positive and negative square root of 2, which is approximated at about 1.4 positive and negative. And there's no multiplicity, so we don't have to worry about relative maximums and minimums on these. All right, I think that's... Oh, we've got one more here, practice problem to give a try. So give it a try. All right, let's talk about it. So here our first term is negative x cubed. So ends are going to go the opposite directions because 3 is odd, and the negative 1 coefficient means the right end goes to negative infinity. And so that's what we've got there. This one, there's a GCF of negative x, so factoring that out gives us x minus 2 times x minus 2. So we do have multiplicity here. So we get 2 zeros of 2. Here it's shown this way. You could also, of course, write it just as your zeros of 0 and 2, 2 would, of course, be fine too. I do that a lot. And so here's our 0 of 2. And with our in behavior, it ends up being at a relative maximum. All right, that ends this particular lesson. So give your assignment a try and have a great day.